Hello everyone. In the previous class, we discussed the foundations for the Smith chart. So, just to recall, Smith chart is nothing but a family of circles on the complex gamma plane. So, that's essentially a bilinear transformation from normalized impedances into reflection coefficient, where we defined gamma is nothing but small z minus 1 by small z plus 1, where small z is the normalized impedance, which is nothing but the actual impedance divided by the characteristic impedance Z0. So we saw that in general, since any normalized impedance can be in general a complex number, it may have a real part R and imaginary part Jx. So when you transform these on the gamma plane, they essentially become a family of circles. So if you recall, the quick take home from the previous class was that if you look at this as a complex gamma plane, where gamma is nothing but u plus jv, we have already discussed how the transformation happens. So just to quickly recap that, the region of interest on the gamma plane is within the unit circle, because for most applications the reflection coefficient can never exceed 1 in magnitude. So that being said, this is the unit circle. May not look like a circle, but just ignore that for the time being. So this is the origin on the gamma plane. So we saw that all the circles corresponding to any given value of R all have their centers on the real axis. So we had proved that for R equals 1, this is the circle. Notice that R equal to 1 means the value of the reactance X can be anything from 0 to infinity. So these two will be on the same point. So as the value of R increases, the size of the circle decreases and the center keeps moving towards the right hand side. We also saw that this point you get when both R and X are 0. So what is the value of gamma at this point? It's minus 1, 0. So therefore, since gamma is minus 1, this point corresponds to short circuit. Now let's look at the X circles. So the X circles, they are all lying with their centers aligned on the U equals 1 line. So the circles will look something like this. We had only drawn some arcs because a large portion of those circles lie outside the unit circle, so they are not of much interest to us. So for example, this is X equals 1 plus 1, and this is for X equals minus 1. So as the value of X increases, the circles keep getting smaller and smaller. Now what is this point? This point is plus 1, 0. So on the gamma plane, gamma of plus 1 indicates this is an open circuit. this point. The outer periphery of mod gamma equals 1 indicates all inductive reactance where the value of X is positive, and the lower periphery or the lower circumference of this lower half circle indicates all capacitive reactances. We had proved this in the last class. So that's how it goes. So the first most important thing to remember is that the Smith chart deals with normalized impedances. When you look at any Smith chart that is available and in use, the U and JV axis will not be shown. Only what will be shown is this family of circles. Because it's understood that the origin is at this point and the axes are drawn along the horizontal bisection line. Now, one very important thing to note is that the Smith chart has a very close relationship with phasors. So, few classes back we had discussed about phasors. What was that? Where we had essentially written the voltage and current in a phasor form. So we had proved that essentially if you want to look at the voltage magnitude, you can treat this as a vector addition of this 1 and this complex exponential. So if this is the unit vector, it lies on the real axis because this is a purely real quantity, and this part mod gamma L times e raised to j phi L minus 2 beta L indicates a circle. So essentially the circle would look like this, where the radius of the circle is mod gamma L and this angle is phi L minus 2 beta L. So we had proved that this is the point at which you get the minimum impedance and this is the point at which you get the maximum impedance. Now, if you notice about the Smith chart, you will see the short circuit point comes to the left and open circuit point comes to the right of the circle which intersects the real axis. So even this position of this maximum impedance and minimum impedance is followed, and with good reason, because essentially this comes as a result of the voltage and current relationship on the transmission line. So now we had proved this, that Z max is nothing but Z0 times rho, where rho is the VSWR and Z min is nothing but Z0 by rho. So in terms of normalized impedances, what would it be? This would be nothing but 1 by rho, and the normalized maximum impedance would be rho. It's as simple as that. Now, when L increases, what does that indicate? L indicates that you are moving away from the load, because we have defined in our transmission line analysis that the load position is the origin, or L equals 0 at that point. So when L becomes more than 0, that means we are moving away from the load and towards the source, because the line from the load to the source is defined as the positive L axis. So now when L increases, the quantity 2 beta L will increase. So therefore phi L minus 2 beta L will decrease. That means when L increases, this phasor angle decreases. So therefore the tip of this vector would move clockwise. Whereas if you reduce L, that means you are moving towards the load, then this angle will increase and the movement will then be anti-clockwise or counterclockwise. So this is something which is very important. If you notice that the point of maximum impedance is coinciding with the real axis, so therefore this value on the normalized plane is nothing but rho, and this value on the normalized axis is nothing but 1 by rho. Now notice one thing, the radius of this circle is mod gamma L. That means if your load is fixed and obviously your line is also fixed, then gamma L will not change. So therefore this circle size will also never change. No matter wherever you are moving on the line, whether it's away from the load, towards the load, whatever it is. You will always be at some point on this circle. Of course, all this discussion is limited to lossless transmission lines, as I had mentioned few classes back, that most of our discussions shall be based on lossless lines. So that it makes our life little simple and that it is not a bad approximation. Now if the load is fixed, gamma L is fixed. So that means even mod gamma L is fixed. Now what are the other quantities we can get from gamma L? We can get the Vswr. So we had defined that rho is nothing but 1 plus mod gamma L minus 1 minus mod gamma L. This is Vswr, the voltage standing wave ratio. So since the gamma is fixed or the gamma L is fixed, our Vswr is also fixed. So this circle is also called as a constant Vswr circle. So next point. Now I am not showing the full axis anymore. Let this be the real axis. let this angle be phi L minus 2 beta L. So in terms of normalized impedances, this is small z max and this is small z min. Now let's take a very special case. Let phi L minus 2 beta L be 0. That means we are at this point. That means we are at the point of maximum impedance. Now, since phi L is constant, beta is constant, let's call this as some L1. Some point on the line where L equals L1 and we are finding the maximum impedance. Now let us move to the point where we get minimum impedance. So let's call it at some point L2. Now what will be the angle? The angle will be pi. Now we are at Z min. So what is the phase change between these two? If I simply subtract the two phase angles, I will get 2 beta L2 minus 2 beta L1 equals pi. Now you know that beta has already been defined as 2 pi by lambda. So now if I know what is L2 minus L1, if I just take it the other way, it means L2 minus L1 is lambda by 4. What does this mean? It means that we are back to the result number 1 which we had inferred by looking at the impedance transformation relationship. What was that? We had said that after a distance of quarter wavelength or lambda by 4, the normalized impedance will invert itself. That means a point of maxima and minima would be separated by lambda by 4, and that is what is happening over here. The distance between Z max and Z min is lambda by 4. We have proved the same thing but using a Phasor approach. So therefore, even on the Smith chart, diametrically opposite points around a constant Vswr circle indicate a distance of lambda by 4. Diametrically opposite points on any constant rho circle indicates a distance or a difference of quarter wavelength distance. So now, if the distance from here to here is lambda by 4, let me just write it over here. Then what is the distance after which I will come back to Z max? It is another lambda by 4. Lambda by 4 plus lambda by 4, that makes a complete circle, which is lambda by 2. And this is also in very much agreement with result number 2 of our impedance transformation. What is that? It is that after every half wavelength, the impedance starts repeating itself. So a movement or one complete movement around any constant VSWR circle is equivalent to moving a distance of lambda by 2, because you are at the same point where you had started. Now with this backdrop in mind, let us take a look at the Smith chart. this is a Smith chart or commercial Smith chart that is available in most shops and what we are going to be using for most of our problem solving. So as you can see, there is one circle. In fact, there are many circles. Now this is the real axis, and this circle, this circle, this circle, this circle, this circle, they all have their centers on the real axis. So these ones which are drawn like this, they are the constant resistance circles. Whereas these circles, this one, this one, this one, this one, over here, this one, this one, this one, these are the constant reactance circles or the constant X circles. Now look at the point, or look at where the first big circle starts, the periphery. That is at this point. So this circle, the innermost of the concentric circles, corresponds to mod gamma equals 1. You have some other markings also, but we will see them little later. If you are convinced or if you are confused, just read what is written over here. It says resistance component or conductance component. Forget conductance. We will look at resistance first. This line indicates resistance component. That means this is the real axis. This center point is the origin on the complex gamma plane. So remember, whatever you do, this is the gamma plane. If you now look at the upper hemisphere, it says inductive reactance component, and down it says capacitive reactance component. So we had proved that all the pure inductors lie on the outer periphery, on the top half, and all the capacitive reactances, the pure capacitors, lie on the outer periphery, on the lower half. So let us understand this Smith chart by taking into account an example problem. Now, you are given a transmission line whose characteristic impedance is 50 ohms. It's a real impedance, and as you know, lossless lines have real impedance, and we are going to use the Smith chart for lossless lines only. And this line is terminated with a load of 20 plus j20 ohms. So let us say, calculate gamma L. This is the first question. Second question is, calculate gamma at a distance of 0.1 lambda from the load. Calculate the Vswr of the line. Calculate the Z at a distance of 0.1 lambda from load. And fifth point, the Z max and Z min magnitudes on the line. Let's do this very simple example. First part, gamma L. Gamma L means what? The load reflection coefficient. So analytically, it is ZL minus Z0 divided by ZL plus Z0. You can do that, or if you want to use the Smith chart, let us see how to do it using the Smith chart. But before we use the Smith chart, the step 1 is convert this load into the normalized impedance. So we will make small ZL. That is nothing but ZL by Z0. That is 0.4 plus J 0.4. Remember, it has no unit. So now comes the fun. Look at this point. This point is gamma equal to 0, or the R equal to 1 point. So this is the point at which you have a match load. So if I want to plot the point 0.4 plus J 0.4, remember the Smith chart is a mapping from Cartesian plane into a gamma plane. It was a bilinear transform, so it's a 1-to-1 mapping. So a unique point will exist at some point on the Smith chart also. So 0.4, let us see where it is on the real axis. So real axis is the horizontal axis. So this is 0.4, you can see. So this is the constant resistance circle corresponding to 0.4. So we need the other half, that is J 0.4. So J 0.4 are these circles or these arcs which are labeled over here on the periphery. Remember, these are reactance curves or reactance arcs. So we have to now look for J 0.4, 0.1, 0.2, 0.3, 0.4. So the point at which the real axis or the R circle meets the X circle is the point that we want. So 0.4 R meets 0.4x at this point. So therefore, we are going to mark over here small ZL. Is that clear? Simple intersection of 0.4 on the real and 0.4 on the J circle. It is a coordinate system. It is a graph. It's just that the axes of the graph are not straight lines, they are circular. Just think of it that way. It is a graph paper only, but the lines are circular, they are not linear. Okay? So now we have found out where is small ZL. Now we need to calculate what is the reflection coefficient at this point. Now before that, all calculations on the Smith chart, you need your geometry sets, that is a ruler and a compass at the very least. So now let's get to business. The Vswr circle is always centered at the origin. Okay, so now the phasor Vswr circle I am going to draw using the radius which is equal to ZL. So this what I have drawn is the constant Vswr circle. Now, how do you find the reflection coefficient at the load? if you remember, the radius of this circle is nothing but mod gamma L. But we have a problem. Even though we are on the gamma plane, the axis is not labeled with respect to gamma L. The axis is labeled with respect to r and jx. So therefore, we cannot find this distance so easily. So fortunately, there are two ways to do it. I'll show you both of them. Notice that below the Smith chart, some linear scales are given to you. Over here, there is something called reflection coefficient P and reflection coefficient E or I. This stands for reflection coefficient of power and reflection coefficient of EMF or current. Now what do we want? We want gamma L. So as we have defined, gamma L is nothing but V minus by V plus. So it's a voltage reflection coefficient. So therefore, we must go for this E or I axis, which goes from 0 to 1. So what you need to do is look at this VSWR circle and look at the point where it is crossing the real axis. So the real axis is parallel to this scale. So all you need to do is drop a perpendicular from this point over here. So essentially you will have something of this kind. A line, perpendicular line, which drops and intersects the reflection coefficient axis, and that will give you mod gamma L. That is one way. The other way, I find it's much more simpler. You simply draw a line connecting the center to the periphery via small z. So now you measure the distance from the circumference to the center. What is that? That is 7.8 centimeters roughly. And you next measure the distance from the ZL point to the center, which is roughly about 3.9 centimeters. And simply take the ratio of this distance to this distance. So 3.9 divided by 7.8 is about 0.5. And if you notice, the perpendicular will also hit somewhere around 0.5 over here. So now we know the first solution, that is mod gamma L, that is 0.5. But as you know, gamma L is a complex term. So how do you find the phase? The phase is what? The phase is nothing but the angle this line makes with the real axis, because that is phi L minus 2 beta L. So here, since we are at the load, length is 0, so this angle will be phi L. And if you notice, angular markings have already been given for you on the outer circles. So either you can take a protractor and measure this phi L, or you can simply extend it over here. So if you see, this angle is roughly about 130 degrees. So phi L is 130 degrees. That means gamma L is 0.5 e raised to j 130 degrees, whatever that is. So using the Smith chart, we have found out what is the reflection coefficient at the load. Let's do the next part. Calculate gamma at a distance of 0.1 lambda from the load. So now we are at a distance, or we are now at ZL. This is the load. Now if you look at the outermost circles, there are two axes which is labeled. One is wavelength towards generator, the other is wavelength towards load. So this wavelength towards generator movement is clockwise, whereas wavelength towards load is anti-clockwise, which we just discussed. So that means if we have to now move a distance of 0.1 lambda, we have to move on this circle clockwise, somewhere on this side, wherever that is. So let us mark which point we are at right now. Look at the wavelength. We are more interested now in moving away from the load. That means towards the source or generator. So at this point, let me call it as L1 is 0.068 lambda. So we now have to move a distance of 0.1 lambda. So where should we end? We should end at 0.168. So where is 0.168? Over here. So that is, I have to now move this way, clockwise. So clockwise 0.1 distance would be over here, 0.1 lambda. So what am I going to do now? I'm going to take my scale and connect the center to the outer axis. That's it. Now after moving, we come over here. This is the point which is 0.1 lambda away from the load, but on the same Vswr circle. Now all you need to do is simply read out what is the normalized impedance. So this is nothing but 1 plus j 1.2. So this would be small z is 1 plus j 1.2. I'm sorry, this is the answer for the fourth question. How do I find out gamma? So if you notice, mod gamma will be the same because we are looking at the same circle. Only what will change is this angle. So angle is now roughly about 60 degrees. So here gamma will be 0.5 e raised to j60. The third question is to calculate the Vswr on the line. So we are moving on the constant Vswr circle. But how to find out the Vswr? We know mod gamma. So what can we do? We can simply say 1 plus mod gamma divided by 1 minus mod gamma. But that's the analytical approach. So that's no fun, is it? What is the use of the Smith chart if we have to do even a single or a simple numerical calculation outside of it? So remember that we are working with normalized values. Now suppose I am on this constant Vswr circle and I am moving away from the load and I come at this point. That is the point at which the Vswr circle first meets the real axis. What is the significance of this point? This point indicates the maximum impedance that you can see on the line. So this is corresponding to Z max. But we just proved some time back that small z max is nothing but rho. So therefore, whatever is the value, we have to read it out. And if you can see, it is 3. So that means we now know rho is 3. As simple as that. To calculate the impedance at a distance of 0.1 lambda from the load, you get the normalized impedance as small z equals 1 plus j1.2. So the absolute impedance is nothing but multiplying it by the characteristic impedance, which will give you 50 plus j60 ohms. Now, the fifth and last question is calculate the maximum and minimum impedance magnitudes on the line. So this point, as I said, corresponds to Z max. And if you keep moving and come to this point, that is the other point where the VSWR circle meets the real axis, this corresponds to Z or small z I should say, because it's normalized. So we know that Z max or rho is 3. That means my small z max is 3. That means my absolute z max will be what? 50 into 3, that is 150 ohms. And z min, you can see from here or from the Smith chart that it is 1 by 3. So that means absolute z min will be 50 by 3 or 16.6 ohms. That's all there is. That's all there is. Now, since we have a little bit of time, let me show you how to calculate the gamma using the dropping perpendicular approach. So you can take any radius, in fact. You just have to ensure that your compass is tightly screwed at all points. This is the 60 degree mark, this is the 120 degree mark, this is the 90 degree mark somewhere. Now over here, so what I'll have to do now is to simply drop the perpendicular and you see on this gamma axis it is touching 0.5. Now notice this point, the center. This is the matched point 1. That means at this point gamma is 0. So the smaller your VSWR circle is, it's better because it is closer to this point. That means the line, if your VSWR circle is smaller with a smaller and smaller radius, it means that it is closer and closer to the matched point. So that is something certainly which we desire. The larger the VSWR circle, the more closer gamma will go to 1 and the more mismatched the line becomes. So today in this brief lecture we have seen how to use the Smith chart with normalized impedances to find out reflection coefficient, to find out impedance. We found out impedance at some point away from the load. Remember, if you don't have a Smith chart, you can always use the impedance transformation relationship. But that is a very tedious job. It's cumbersome to solve so much of mathematics when you can actually get it from the Smith chart. So we saw this also. We saw how to get the reflection coefficient. We saw how to get the impedance at any point. We saw how to calculate the Vswr. We saw also how to calculate the maximum and minimum impedance values that can be seen at any point on the line. Now here is one point which I would like to say. Notice that the density of coordinates on the Smith chart are different. The spacing is a lot over here, while the grids are closer over here. Plus we are using geometrical instruments, and manual human error can definitely introduce some error in our calculations. But as an engineer, our first priority should be to get a quick solution, a quick estimate. It may not be 100% accurate, but it should give us a very good idea. So for such solutions, a very quick solution which is not 100% accurate but 90% or above, Smith chart is definitely very good. It gives you a pretty accurate estimation of your results. However, if you want more accuracy, you have to sacrifice time and efforts, and then the only option is to use those formulae like the impedance transformation formulae or those voltage and current formulae which we have derived. So with this, I have introduced you to the Smith chart, and I hope that this shall be used in a very effective manner to solve problems henceforth. Thank you.